Hey everyone, and welcome. Are you ready to completely upgrade how you see the world? Today, in this explainer, we're moving way beyond simple guessing games. We're diving deep into the true mathematical science of predicting outcomes. We're talking about probability, specifically the theoretical approach from your curriculum. Get ready because things are about to get really interesting. Okay, look at this quote. R.S. Woodward called the theory of probabilities a formidable body of great mathematical interest and practical importance. Now, why would he say that? Well, because probability isn't just about flipping coins or rolling dice at game night. It is a profoundly powerful tool. It's literally what scientists, engineers, and researchers use to understand, measure, and navigate the very real uncertainties of our universe. Which brings us to a massive question. How do we predict the unpredictable? Think about it. How do engineers figure out the failure rate of a multi-million-dollar satellite launch? Or how do we measure the risk of a skyscraper collapsing in an earthquake? The catch here is we absolutely cannot repeat those massive, expensive events over and over just to get data. That's just not possible. We need a different way. And this is exactly where we level up from what you learned in 9th grade. Back then, you learned empirical probability. That meant finding the probability by actually doing the experiment, like sitting there and physically tossing a coin 100 times. But like we just said, you can't crash a satellite 1,000 times to find its empirical probability of failure. It's too expensive, right? So the genius solution for 10th grade is theoretical probability. By making logical assumptions about equally likely outcomes, we can calculate the exact probability directly using math without ever crashing a single satellite. So here is the absolute core of it all, the formula for theoretical or classical probability of an event, which we write as P of E. Let's break this down together. The E stands for the event we're hoping for. The numerator, the top part, is the number of outcomes favorable to our event E. And the denominator, the bottom part, is the total universe of what could happen, the number of all possible outcomes. And remember, the super important assumption holding this whole thing together is that all outcomes are equally likely. Let's anchor this with a really intuitive example. Imagine Kritika has a bag, and inside there are exactly 3 balls of the exact same size, 1 red, 1 blue, and 1 yellow. She reaches in and pulls out a ball without looking. Because they're the same size, grabbing any of them is equally likely. So what's our total universe of possible outcomes? Just 3. And what is the favorable outcome for picking the yellow ball? Exactly 1. Therefore, the probability of drawing the yellow ball is 1 divided by 3, or 1/3. It's simple, elegant, and perfectly logical. Section 1. Beyond simple coins. Visualizing sample spaces. Now, picking a single ball out of a bag is pretty easy to hold in your head. But what happens when the universe of possible outcomes gets a little more complex? Let's build this out. Imagine you have 2 standard dice in your hands, a blue die and a gray die. You're going to throw them at the exact same time. The question is, what is the probability that the sum of the 2 numbers appearing on top is exactly 8? To solve this without just guessing, we need to mathematically construct our entire universe of possible outcomes. Here's how we do it. If the blue die shows a 1, the gray die could show a 1, 2, 3, 4, 5, or 6. If the blue die shows a 2, the gray die can again show anything from 1 to 6. If you map out every single possible pair, you create a 6x6 grid. By physically drawing out this sample space, it instantly becomes super clear exactly why our total number of possible outcomes, our formula's denominator, is 6 times 6, which is 36. Now look at how visual the math becomes here. We are hunting for a sum of 8. Let's find our favorable outcomes on the grid. 2 plus 6, 3 plus 5, 4 plus 4, 5 plus 3, and 6 plus 2. Do you see that brilliant diagonal pattern they make? Count them up, and we have exactly 5 favorable outcomes. So our theoretical probability of rolling a sum of 8 is simply 5 over 36. Boom, you've got it. Section 2. The boundaries of reality, impossible and sure events. Let me throw a trick question at you. What happens if we look for an outcome in our dice grid that just literally breaks the laws of reality? What if the event is mathematically impossible? For instance, what's the probability that the sum of our 2 standard 6-sided dice is 13? Well, the highest possible roll is a 6 and a 6, which is 12. There are absolutely 0 favorable outcomes for 13 anywhere in our grid. This is what we call an impossible event. Mathematically, it's 0 divided by 36, which is exactly 0. It will never, ever happen. On the flip side, what is the probability of getting a sum that is less than or equal to 12? Well, looking at our grid, Every single one of our 36 outcomes fits that description. That's 36 favorable outcomes out of 36 total outcomes. And 36 over 36 is 1. We call this a sure event or a certain event. It is 100% guaranteed to happen, and it represents the absolute ceiling of our probability scale. Remember this, probability always lives between 0 and 1. Section 3. The rule of complements. Event E versus not E. Okay, let's see how these rules build into one of the absolute best shortcuts in math, the relationship between something happening and that exact same thing not happening. We call these complementary events. Let's say event E is flipping a coin and getting a head. What's the opposite? It's not getting a head, which obviously means getting a tail. We denote this not E with a little bar over the E called E bar. An event and its complement make up the two halves of a whole reality. One of them absolutely must happen. Because it is a sure event that either E or not E is going to occur, their probabilities must add up to exactly 1. Mathematically, the probability of E plus the probability of not E equals 1. And this gives us an incredible shortcut. If you know the probability of an event not happening, let's say it's 1/4, you can just subtract it from 1 to quickly find the probability that it will happen, which would be 3/4. It's such a brilliant time saver. Section 4. A curveball, continuous probability. You guys are doing fantastic so far. But I have to tell you, while we've totally mastered finite, countable outcomes like dice and coins, the universe sometimes throws us continuous curveballs. Sometimes outcomes aren't nice, neat, countable numbers. Sometimes they are uncountably infinite. Imagine a map showing a rectangular forest with a lake in the corner. If a helicopter randomly makes an emergency landing somewhere within this entire region, what's the probability it lands specifically in the water? We can't count individual outcomes here because space is continuous. So instead, we use geometry. We simply divide the total area of the lake by the total area of the forest. The core logic of probability, favorable divided by total, stays exactly the same. It just visually evolves. All right, let's rapidly lock in everything we've just conquered. These are your absolute golden rules of theoretical probability. Number 1, probability is favorable outcomes over total possible outcomes. Number 2, your answer will always be a fraction or decimal between 0 and 1. Number 3, a sure event is exactly 1. Number 4, an impossible event is exactly 0. And number 5, the probability of an event plus the probability of its complement, not E, equals 1. Master these 5 pillars and you've got a rock-solid conceptual foundation for this entire topic. So I'll leave you with this final thought. We started out by asking how we predict the unpredictable without endless costly experiments. Well, if theoretical math and the logic of equally likely outcomes can accurately predict a satellite's success before the thrusters even ignite, what else can we predict about our world using math? I really encourage you to look around today and try to spot the hidden mathematics of probability governing the world around you. Thanks so much for joining me on this explainer. Keep practicing those equations, and I'll catch you in the next one.
Welcome to this explainer. Look, if you're gearing up for the highly competitive Karnataka SSLC board exams, you are exactly where you need to be right now. Speaking to you as a veteran board evaluator, I'm going to show you exactly how to crack the Chapter 14 probability marking scheme. Now, we're not going to sit here and relearn basic definitions, right? You already know those. What we're doing today is maximizing your marks on paper. I'm going to show you exactly what the evaluator's red pen is actually looking for.
Because here's the thing, I don't just want the right answer, I want the right steps. As an examiner who's personally corrected thousands of math papers, let me let you in on a little secret. Jumping straight to the final fraction? That's exactly where brilliant students throw away their marks. You might know in your head the probability is 1/2. But listen, if you don't show me exactly how you got there, I literally cannot give you full credit.
So here is your insider's playbook. First up, we've got the 1-mark MCQ traps. Second, we'll decode the 2-mark formula. Third, we'll hit high-yield coins and dice. And fourth, I'll give you the evaluator's final checklist. Let's get moving.
All right, part 1, the 1-mark MCQ traps. Let's secure those quickest wins on the paper and dodge those annoying little pitfalls that routinely catch students totally off guard in the multiple choice section.
Okay, flash this number in your mind right now. 0. 0 is the absolute probability of an impossible event. Guys, this is an absolute favorite 1-mark direct question for the evaluators. If the board asks you for, say, the probability of rolling an 8 on a standard 6-sided die, do not overthink it. The answer is 0. Lock it in and move straight on.
Now, on the flip side, what about the probability of a sure event? Well, it's exactly 1. For example, if they ask for the probability of rolling a number less than 7 on a standard die, boom, it's 1. Lock this in to secure another instant mark on those MCQs. And just a quick reminder, probabilities never, ever go below 0, and they never exceed 1. Keep that in your back pocket.
Now, beware the classic complementary event trap. You've seen this straight out of your textbook exercises. If a question tells you P of E is 0.05 and then asks for the probability of not E, don't freeze up. Immediately subtract it from 1. Just do 1 minus 0.05, which is 0.95. We usually write this not E as an E with a little bar over it. Just always remember your golden rule here. P of E plus P of not E always equals 1.
Moving right along to Section 2, decoding the 2-mark formula. Let's explicitly break down the anatomy of a perfect answer, according to the official SSLC key. This right here, this is where you transform from just being a good math student into a strategic, exam-cracking machine.
Look at this official model answer key straight from the board. Look really closely at the half-mark allocations on the side there. As an evaluator, I'm awarding a half mark merely for stating the sample space S, and another half mark just for writing down the formula. And that's before you've even done any real math. Think about that. If you just write down the final fraction, you are basically throwing away 50% of your grade for that specific question. No way we're doing that.
So, here is your crucial 4-part official grading rubric. Step 1. Explicitly write your sample space S and the number of outcomes N of S. Bam, that's a half mark. Step 2. Write your event A and N of A. There's another half mark. Step 3. Write out the official formula. Probability of A equals N of A over N of S. Half mark. And finally, Step 4. Write your final simplified fraction. Memorize these 4 steps, because skipping even one is literally giving the evaluator permission to deduct your hard-earned marks.
Let's compare 2 different approaches here. The trap is the rush student. They correctly calculate the odds of flipping ahead. They write down a naked fraction 1/2, and they walk away with 1 out of 2 marks. Tragic, right? But the key to full marks, that's writing S equals HT, N of S equals 2, and the formula P of A equals N of A over N of S. And now that is a perfectly structured board answer that scores 100%. You need to be that second student.
All right, Section 3, high-yield coins and dice. Keep a really close eye on these next scenarios for your 3-mark written questions, because these are the board's absolute favorites. When you face a 3-coin toss question, do not hesitate. Your N of S is exactly 8. And listen, you must physically list out these exact 8 outcomes to trigger that first half mark from me. A really great memory trick is to just group them. Start with all heads, HHH, then all tails, TTT. Then systematically move the tails around, HHS, HTH, THH, and then do the same for the heads, TTS, THT, HTT. Take a breath, write them all out, perfectly, every single time.
Now, what about those double dice questions? Suddenly, your sample space jumps to 36. You'll want to mentally recreate this official textbook table when you're sitting in the exam hall. And hey, if there is only one thing you remember from this, remember the sum of 7 rule. The sum of 7 has the highest probability of all outcomes, sitting right at 6 out of 36. Seriously, memorize this quick mental breakdown as a visual shortcut. A sum of 2 or 12? Well, that's just 1 out of 36 each. A sum of 7? That's your peak, that's 6 out of 36. A sum of 9? 4 out of 36. Having these specific benchmarks locked in your head will let you instantly verify your dice sum fractions under intense exam pressure, so you don't have to draw out a massive 36-item grid every single time. It's a huge time saver. Okay, bringing it home with Section 4, the evaluator's final checklist. Let's lock in everything we've just talked about so you can walk into that exam hall feeling totally prepared.
I want you to take a mental screenshot of these absolute non-negotiable rules. 1. Never ever skip writing the formula. 2. Always explicitly list out the sample space elements inside those curly brackets. 3. Use that complementary event formula for rapid calculations in your 1-mark questions. And finally, 4. Never leave a fraction unsimplified. If you get 6 over 36, you better reduce that to 1 over 6. Follow these rules, and you effectively error-proof your paper against the most common mark traps out there.
By deeply understanding this official marking scheme, you're no longer just, hoping for a good grade. You are structurally engineering a perfect 80 out of 80 on paper. You now know exactly what the evaluator's pen is searching for. So the real question is, the next time you look at a math problem, are you just seeing a bunch of random numbers, or are you finally seeing the underlying blueprint to full marks? Go out there and dominate that exam paper. I'll see you in the next explainer.